A-level maths student here, proof of differentiation by first principle for the graph y equals x cubed. Okay, so to start, let's draw the graph. I'm sure you all know what it looks like, but we need to visualise it. We've got an x-axis and a y-axis. The graph, it curves upwards on the positive side and then goes downwards on the negative side. So if we were to find the gradient from point P of a tangent that we've drawn on, how would we do it? Well, first, what we've got to do is we've got to try and figure out what the gradient would be if it was, or what the gradient between 2 points would be. So let's call the points point P and point Q and draw a gradient triangle. Now, because y equals x cubed, we can draw P's coordinates as x cubed. I hope you can follow that. Q. What are Q's coordinates? Well, let's construct the line PR. It's an imaginary line. And so let's just call PR an arbitrary length h. There's no set length for it. We're just going to call it h because because it represents any value. And we'll call QRL, though it's not really that important. So the x-coordinate for R is x plus h. And let's just call the y-coordinate YR. Q is vertically above point R, so it will also have an x-coordinate of x plus h. Substituting y equals x cubed with it being on that line, I'm sure you can see why the y-coordinate is x plus h all cubed. So now we're going to think about the formula m equals y1 minus y2 over x1 minus x2. And we'll substitute our two values for y1 and y2 in, and our two values for x1 and x2. So, as you can see, what we have is the gradient is x plus h all cubed minus x cubed. And for the denominator, we've got x plus h minus x. So it's x plus h all cubed minus x cubed over x plus h minus x. I hope you can excuse the jump there. I expanded x plus h cubed incorrectly, so didn't want to include that in the video. So let's just expand it now. It's the same as x plus h times x plus h squared. You should know that from your indices rules in GCSE. So let's just create a grid now for expanding it. If you're comfortable with expanding cubic brackets, then you might want to skip this video or write down the exact place to skip it to in this in the description box. Here, when we have x squared plus 2hx plus h squared, I hope you can see that that's x plus h squared expanded. So now we're just timesing, well, in case you don't know how this works, you've got x squared is in the left column and x is in the top row. So the box which corresponds to the left column and the top row is x times x squared. And you end up with the value x cubed plus 3x squared h plus 3x h squared plus h cubed. You can see I've forgotten to add on the minus x cubed there. Now, as you can see, the x and the minus x cancel each other out. I've forgotten to cross the minus x out. And the x cubed and the minus x cubed also cancel each other out, because any value take away itself is 0. So now what you end up with is 3x squared h plus 3x h squared plus h cubed divided by h. And because all these terms are divisible by h, we end up with 3x squared plus 3hx plus h squared. Okay, so now I'd quite like to look back at our diagram at the start, just so that we can visualise this as an image. So this tells us the gradient between 2 points P and Q, 3x squared plus 3hx plus h squared. So if we were to have increase h, the gradient might be further than what it would, but if we were to decrease h, it becomes a lot closer to the actual gradient at Q, the gradient of the curve. Well, the curve at that point. So what we can say is, what is the limit as h gets increasingly small? What is the value of m when h is so infinitesimally small that it's virtually indistinguishable from x? So x plus h is virtually the same thing as x. Well, h would tend towards the value 0. 3x squared wouldn't change, it would just be 3x squared because it doesn't incorporate h. 3xh would tend to 0, and h squared would tend to 0, because anything times by 0 is 0. The gradient itself then, considering all of its components, would tend towards 3x squared, which is what you get using the formula for differentiation. Just to explain where the notation for dy over dx comes from, the correct notation when doing first principle is delta y and delta x. Delta means small changing. I didn't use it in this video as it's quite confusing notation. Dy is represented of the limit as the limit of delta y as delta x tends to 0, and dx is an infinitesimally small value of delta x. So, in conclusion, when y equals x cubed, dy over dx equals 3x squared. That is, the gradient at any given point is equal to that point squared times 3. If you're interested in understanding this a bit further, you might want to derive it yourself for y equals x squared. Also, you could check out my video for y equals x to the n and how you get the result dy over dx equals nx to the n minus 1. I'd also recommend teaching it to someone because that's a really good way to remember it yourself. Thank you for watching. Remember, this is A-level maths student. That's my account name, and I hope you watch some more of my videos. Bye!